Alright, welcome to the next video on fundamentals of strength of materials. Today we'll be calculating a simple example of tensile stress. So here I have a simple example. We have there an task: calculate normal stresses in cross sections and change of the length of the shaft when material is the structural steel S355, which Young's modulus is 210 gigapascals. The structure is as shown in here. So you can see we have there two round bars. They are connected together, and they're also connected into the wall. We have two loads there. We have 20 kilonewtons here, and we have 5 kilonewtons in here. The diameter of first section is 20 millimeters, and the diameter of the second section is 6 millimeters. Lengths are as shown here, 300 and 250. Now for this calculation we are going to need two basic formulas, which both are included in the set of formulas which is available on Moodle. We need the formula for normal stress. Sigma equals to N, so the force, normal force, divided by the cross-section area. And then the formula for the change of the length, delta length, change of the length, equals to normal force times the length of the section divided by the cross-sectional area of the section multiplied by the Young's modulus of that material. So first things, always when we want to start making these calculations, is that we need to do the free body diagram. You should be familiar with how to do the free body diagram, free FBD, we call it. So we're going to create the FBD first, right? So let's start by drawing this piece of material. So it's like so. Oops. Let's try again. Let's try that again. Like that. Let's clean it up a bit. So now we have forces in here. We have a force in here. Let's change the color of the pen to red. So we have here a force pulling this way. Then we have a force in here, but this one is compressing or pushing from here. This one is 5 kilonewtons, and this one is 20 kilonewtons. And now on this side here, we know that we are going to be needing a force which will support it from here. So F A X, like that. In the task, the support in here is that it's completely fixed on the wall. So basically in here we also have forces in y direction, F A Y, and we also have the moment in here, a moment A. Right? Well, what happens next? When we have an equilibrium state, so we know that this part is in equilibrium state, we can form the three equilibrium formulas, which are as follow. So we have equilibrium. Let's change the color once again. So what we have is that the bar must be in equilibrium, the forces in horizontal direction, the sum of all the forces has to be 0. Also, the sum of all the forces in vertical direction, they also must be 0, right? And thirdly, the third equation is that the sum of all the moments in any point must equal to 0. Well, in this case, we basically only have horizontal forces, and hence these two equations are basically not necessary, but we can write here that F A Y equals to 0 and M A also equals to 0. Now finally, let's do the first equation. So F A X minus 20 kilonewton. Like here, you can see, here we have the FA in the X direction. It's here. It goes from left to right. Okay, so that's positive here. And then we have 20 kilonewtons, which is from right to left. It's negative. And then finally, we have the 5 kilonewtons at the end, which is to positive direction, plus 5 kilonewtons here. And this all has to be 0. I like to give these equations numbers, so when I'm solving things I can mark that which equation I'm using. So 1, 2, 3, like so, respectively. So now we have 3 equations there. Well, if we take a look at these equations, we can quite easily see that, okay, these two are unnecessary, and from the first one we can very easily solve the FAX. I like to mark here that from equation 1 we solve that FAX equals to 20 kilonewtons minus 5 kilonewtons equals to, and that is equals to 15 kilonewtons. Like that. Well, now we have calculated the force that is at the left hand side of this bar. So what is the next step? What is the next step that we always want to do when we are talking about internal loads? We want to draw the normal stress diagram. I highly recommend that you leave space below your free body diagram. For me, at least, it's best place to draw the normal force diagram is below the actual free body diagram. So I start by drawing this kind of graph in here. In here we have the normal force. Let's make a little more room here. So when we start drawing the normal force diagram, we start from, in this case, we start from the left hand side. And on the left hand side we can see that at first the force, the normal force, is going to 15 kilonewtons. We have the FAX, so it's gonna jump to 15 kilonewtons. It remains at the level of 15 kilonewtons until we reach this point. from here we have another force that comes to play. It's 20 kilonewtons and it's from opposite direction, which means that it will reduce the force by 20. So the normal force within the bar will drop down, and it will drop down to level 5. Okay? So now we are at level 5. And from this point forward, it will remain on the same level until we reach the end, where the last force, the 5 kilonewtons, will make it to 0. So if you did everything correctly, you should end up, when you do this normal force diagram, at the end you should be back at the 0, right? So in here we jumped from 0 to 15. Let's draw it in here. Let's take the pen. So we are at minus 15. So we are compressing, and therefore the normal force is minus 15 kilonewtons, like that. So we can mark here also minus. And then in here we go to 5. So we can mark here, we are at 5 kilonewtons here, and it's positive. I like to mark it like this, so it's more clear to visualize where the graph goes actually. So now we have done the normal force diagram. Well, next thing to do is to convert this into stresses. So we must calculate the stress for each section of this part separately. Why? Because the diameters are different and the normal force is also different in different parts in here. So let's start with the part section 1. So we call this one is the section 1. Let's mark it here, section 1. And this one is the section 2, like that. So let's start from section 1. So the stress, the formula for stress is sigma. Let's mark it sigma 1 here, is the normal force 1 divided by cross-sectional area 1. And in this case it means the normal force was minus 15 10 to power 3 newtons divided by the pi times the radius, which was 10 millimeters, to power 2 millimeters power 2, and this will equal to minus 48 megapascals. Right? And then for the section 2 we do the same thing. Sigma 2 equals to n normal force at section 2 divided by the cross-sectional area at section 2, which will be 5 times 10 to power 3 newtons divided by pi times 3 power 2 millimeter power 2 equals to 177 megapascals. So what have we done so far? So now we have calculated the internal normal stress, and then after that we have also calculated the internal normal load, and then we have calculated normal stresses here. The last thing is to calculate the change of the length. So delta L1 is N1 times L1 divided by A1 Young's modulus 1, like this. It's the formula from your sheet, and the result will be minus 0.067 0.82 millimeters. And for the part 2 delta L2, the same thing will be 0.2105 millimeters. And the total change of the length will be the sum of delta L1 plus delta L2 equals to the sum of these two things, which will be 0.1423 millimeters. So that's how it's calculated. Alright, hope you could follow up, and please try it yourselves. See you on next one.